I'm going to use GeoVisionary, our software, to show you our science strategy for the next decade. And we're calling that strategy the Gateway to the Earth. And in the strategy, we're essentially responding to three challenges: resources, resilience to natural hazards, and climate change. And I'm going to show you three areas in which BGS is responding to these challenges. The first one is shale gas. Now, the UK may have a shale gas resource. We're flying in now to what a shale gas rig might look like in the landscape. Shale gas might offer us jobs, it might offer us cheap energy, but there are also environmental hazards that could be associated with shale gas, like water contamination or like earthquakes. And so we have some science to do to understand these challenges. And we also need to know how much shale gas there is in the country, which we don't know precisely at the moment. So what I'm going to show you now is how we looked at the amount of shale gas in the country. This map shows the geology, and that red line shows you the area we think is most prospective. But you can immediately see that this is cities, and it's motorways and national parks and high-value agricultural land. So that's the major challenge of shale gas. We're a densely populated country. But this image here shows you a 3D model of the shale under the north of England. This is the Bowland Shale, and we're flying along now as if the whole of the rock between the shale and the surface is transparent. And you can see where the colour is red, that's where the shale is thick, and where it's yellow and blue, that's where the shale is thin. And we've also voxelated this model, so we've cut it into blocks so that we can use those blocks to have attributes given to them, like porosity and permeability. So we should be able to model the way that the shale behaves, the way fluids flow through the shale, the way gas flows or frac fluid. We can also flex the model to see only the thick parts and the thin parts. And as we fly in, we can even have a look at what the surface looks like, the top surface of the shale. And finally, we can even show what the gas rig might look like. And here you can see the gas rig perched above the shale, a couple of kilometres above the shale, where the drill might hope to get gas out. So this shows you how we can use 3D geological models to understand the resources underneath our landscape, to know how much gas there is, and to understand something about how safe it is to extract. But at the moment it's very difficult to say whether shale gas could be a business in this country. We simply don't know at this stage. But we will be taking our expertise to other parts of the world to understand shale gas resources elsewhere. Now, the next example I'm going to give you is about groundwater flooding potential, or groundwater flooding susceptibility. And what you see now is a geological map, not really of rocks, but of the susceptibility to groundwater flooding. And the most important colour is the yellow, and that's the highest groundwater susceptibility level. You can see this is actually following the Thames, so you can see areas where groundwater, which is water that comes up from the rocks below and floods into fields and along the fields next to rivers and in towns next to rivers. And it's been a real problem in London. You can see London now in the last few months, particularly over the winter, when a lot of groundwater flooding happened. This is a very populated area, so it's clearly a challenge. Now, another clever thing about the GeoVisionary software is that we can focus on big things and small things at the same time. So now we're going to focus in on a particular part of London. This is actually Hampton Court Palace. So it's a loop of the River Thames, which you can just see here. This big loop, and over to the left is Hampton Court Palace. And using this software, we can simulate what a flood looks like. So if the Thames begins to flood, we can make it look like that. At this stage, we're not sure what the proportion of ordinary river flooding to groundwater flooding is. And this is a very important science question. particularly west of here in London, around Windsor, where it's clear that the chalk, which underlies much of London, actually supplies some of the groundwater flooding. So to understand why groundwater flooding has happened, and to be able to forecast and predict it, we have to understand more about the chalk. And what this shows you here is a fantastic database underneath London, which we've constructed out of 20,000 borehole records. And these are over 100 cross-sections of the geology under London. We're flying over London now, and we can see these cross-sections. The purple colour is the London clay, and the green colour is the chalk. And we're going to use this fantastic database to make a 3D geological model of the chalk. We'll voxelate it, and we'll be able to model the way that groundwater develops, the way it moves, and the way it flows out onto the land. So an example of BGS using its 3D model to help people's lives and livelihoods and understand the effects it has on people's lives and livelihoods. Now the last example, we're going to fly eastward to Yorkshire. And what we're going to look at here is a receding coastline. This is an example of what we're interested in terms of climate change. What you can see here is a LiDAR laser image of a receding coastline where the coast is being eroded away. And this is a very precise image, which again we can hold in geovisionary, a 2 centimetre pixel. And we know precisely how the coast is getting eroded here. And we're using that information to understand how other coasts will erode, both in the UK and abroad. And finally, you might ask what might be different about the BGS in the future. Well, I've been talking a lot about forecasting and predicting. And in fact, to be able to do this really well, we have to understand the Earth better, which means we have to instrument and observe and record the Earth better. We have to be able to do it in real time. And what geological surveys did in the past essentially was collect information about coal or oil or tungsten or tin. What we did with that information was we made geological maps like this one here. And then we realized that geological maps, which are quite a good way of representing information, could be improved as well by making 3D models. And this is a 3-dimensional model of the Olympic site. And that's a very good way of representing geological information. But we want to use these 3D models, of which we have a lot, essentially to understand flow within the models and to be able to predict and forecast at timescales that matter to lives and livelihoods, to matter to people. And what I'm going to show you now is an example of what this might look like. Now this is an example of a place where we might have very dense usage of the surface and the subsurface, industrial usage and other kinds of usage. And as the land fades away, we'll see this 3D image, which is showing dense use of the surface. We've got factories, power stations, we've got a landslide there, we've got an oil and gas rig appearing here. And as we fly around, you can see a coal power station using carbon capture and storage. And we've got farms and lots of agricultural land. This is an example of a place where there's a lot of use. And here we have a radioactive waste disposal facility as well. And the purple line shows a shale gas well. And we can see that not only is the surface being used a lot, but the subsurface is being used a lot as well. There's a lot of dense usage of the subsurface. So really, to be able to do this properly, to manage the subsurface, to make sure it can be done safely, and so that we can get the most that we can out of the subsurface, is to monitor and record and model it in much more detail and much more sophistication than we've done before. What this means is that we'll start to monitor in boreholes in real time. We'll start to measure and monitor in real time. So in the next decade, BGS will research the science of subsurface flows and interaction between flows and the solid rock matrix at timescales consistent with human usage of the subsurface. What this really means is we'll be doing geology at timescales that matter to people, not hundreds of thousands of years or millions of years, but days and hours. So in this image you can see we have someone canoeing down the street near the Thames. In the future we'd hope to be able to predict and forecast whether groundwater flooding is going to happen and other kinds of activity like that. So in conclusion, the BGS is a big organisation. We cover most of the geological sciences. We're equipped for long-term strategic research in the national good. In the years to come, we'll move towards understanding subsurface processes at timescales that matter to people. And I think this is precisely what a geological survey should do in the future. And in the future, we'll take all this expertise and knowledge, our modelling, our instrumentation, forecasting, predicting and modelling, to other parts of the world where this kind of understanding also has to be applied.